Hello, welcome to another John Brooks technical webinar. My name's Stefan Fediw. I work for the John Brooks Company, and we're here to speak about today hunting problem systems. With me is, as usual, Chris Chapman. How are you doing, Chris?
I'm pretty good, thanks. On this definitely full, dreary, wet day.
Yeah, well, only in Ontario. Maybe somewhere else in Canada it's better. That's for sure. Did you like the exploding pumps, Chris? Was that pretty cool?
Very good, very good.
Thanks. I appreciate that. Okay, your mics are going to be muted as usual, but if you have any questions at all, just fire them into the chat box down there, and Chris will look for them. So let's get started here. Who's John Brooks? We were established in 1938. We're a privately held Canadian company. We have over 200 of us across Canada. And we're a full-service national supplier of filtration, spray nozzles, custom skid packages, specialized valves, and pressure vessels. And as always, if you have any technical inside training that you need, any presentations that are coming up, involving pumps, hydraulics, filtration, pressure vessels, spray systems, heat exchangers, give us a shout, and we'll see if we can meet up and do a presentation for your organization free of charge. Okay. Today we will be covering troubleshooting, making sense of gauges, duplex pump systems, dissimilar pump systems, more troubleshooting, and finally, if we have time, selection of system curves without calculations. First, we're going to be talking about a lot of maintenance and hands-on subjects here. So we're just going to say this warning right now. This presentation should not replace any recommendations made by a specific manufacturer. Operational manuals should always be consulted, and any specific questions or concerns should be addressed to the specific manufacturer. Okay, so troubleshooting. Troubleshooting / startup commissioning. They're all very much related. What you'll always need is the manual itself. A lot of information in these manuals. Right here, usually there's some hydraulic information, which is wonderful stuff. You won't be able to troubleshoot without, in the pump case, a pump curve. Then there's usually some cautions, some safety aspects, which are great to review each time. And finally, some installation, pre-installation checklists. And even today, if I know I'm going on a troubleshooting situation, let's say tomorrow morning, I will still pull the manual and I will have a quick 5-minute read through the troubleshooting charts. And most manuals for most pieces of equipment have this trouble, possible cause, and probable remedy. And it's really important, even though, I've been dealing with some of these pumps for several decades, it's still nice to just get your head around, hey, get your mind in that space of troubleshooting. Suction and discharge gauges. If you're involved with pumps, moving fluid, suction and discharge gauges are the eyes inside the pump. Here we have a suction and discharge gauge. Normally a nice quarter-turn ball valve is a wonderful piece of equipment that's on these. That way we can isolate the gauge, and it doesn't always have to see the pressure or the vacuum all the time. We can open them up when we're looking to read them, and then close them down again. They don't need to see the pressure all the time. You'll save the valves that way. Sorry, the gauges that way. So traditionally, I think most people think of gauges as measuring the pressure developed by the pump, and that is true. But from a troubleshooting perspective, there's another way to think of gauges. Gauges measure the static and frictional losses of a piping system. This is also true, and it is many times an improved definition for troubleshooting a system. So keep that in mind. If you're going to take away just one thing from this seminar today, this webinar, it is the following. Discharge gauge minus the suction gauge reading will always give you the total dynamic head of the pump. We'll speak about that a little bit later, but discharge minus suction, turn off your common sense, just do that and you'll be fine. And speed detection, you need some kind of a probe, usually either a contact tachometer or a light probe right here. And make sure that you are tacking the actual pump speed. In this case, we're tacking the motor speed, but because it's flex coupled, it should be one and the same. If not, make sure you tack the pump itself if you don't, if the pump and the motor could be running at different speeds. Again, keep those guards on. If you can do all this with the guards on, it is definitely recommended, and read the manual. And obviously that's going to tell us where we're operating. If we know the speed of the pump, then we're going to know what operational curve we're going to be operating on. And amperage voltage measurements. This is really crucial, very, very important for submersible pumps, but also any electric pumps, electric driven pumps anyway. So here's the motor. You have your multimeter here. And there's a few things that we want to get out of this multimeter, out of these measurements. And one's called BHP, or brake horsepower. And all what brake horsepower means is horsepower or power consumed. As soon as you put the brake in front of it, it means it's being consumed. So I could have a 20 horsepower motor nameplate, but its brake horsepower in a particular situation could only be 10 maybe. So that means it's a 20 horsepower motor named, but the brake horsepower, what's being consumed, is only 10 horsepower. So brake horsepower is consumed horsepower. And here is the equation for it: volts, amps, power factor, motor efficiency, and some constant. Depending on the units, you could be in kilowatts, brake horsepower. One of these right here, the power factor, the PF, that's something normally we can't get at too easily. An electrician might be able to give it to you, or the plant facility. So there's a little bit, there's another equation here that's not as accurate, but it's things that we can grab on site, and therefore it makes it very useful. If we have a multimeter and we have the nameplate of the motor, which we should, then amps and volts come from the measurement, AM, amps measured, volts measured, and horsepower, NP, nameplate, full load amps nameplate, and voltage nameplate. Put all those together and you get a pretty good accurate, pretty accurate anyway, value for brake horsepower. What is being taken from that motor? What is being consumed as far as power goes? And there's many reasons to be a Canadian. It's great to be a Canadian. One of those is, for the most part, for many parts of Canada, we use 575 volt voltage power supply, three-phase power supply. And it just happens that the brake horsepower approximately for a 575 volt three-phase NEMA motor roughly corresponds to the amperage reading. So if I've got a 30 horsepower motor and it's pulling 20 amps at 575 volt three-phase, you're going to be pulling about 20 horsepower. It just seems to work out that way at that 575 volt. Finally, keep an open mind. Chris, how many times have we been on a startup over the decades and we thought it was going to be a 5-minute job, and what did it turn out to be?
Yeah, it turned out to be longer because you assumed that everything was going to go right, or you assumed the valve was open and in fact it was closed, or something simple.
Something very simple. Keep an open mind. Chris, what am I looking at here?
Oh, I would say that's a face looking at me.
Yes. Because we made an assumption, it's actually a face it was a face that was looking away from us. Just a simple idea that sometimes common sense to me is a very scary word. A lot of things that are common sense, it just means that you've made a few assumptions. So just be very careful when you're troubleshooting. Get the value down. You can't take people's words for things. Check it out yourself. If they say a valve's open, make sure it's open. Make sure the handle on a valve isn't reversed so it looks open, but it's actually closed. We've had that, right, Chris?
We have, yes.
There's a lot of things that can happen. Many times the problem was something simple. Just keep an open mind. So general inspection. When we first get to site, we have a brand new pump here. Whether you're an operator, commissioning, or troubleshooting, you're going to know a few things. What's the function of the pump? Is it a booster pump? Is it emptying a well? You know, what is it doing? What's the functionality of the pump? Understand the system, the pipe. Where does this pump to? Where does it pump from? Are there any filters? Are there any valves, heat exchangers? You know, essentially walk the system. Take a look at it. Get to know the system. It's time well spent. Fluid being pumped. What is it? Is it high in temperature? Is it really cold? You know, are there solids? Is the pump ready to start? Lubrication levels, are they all okay? Oil, grease, are they, you know, a lot of times equipment is shipped without oil or other lubricants. Is it primed? Does it need to be primed? Isolation valves, where are the isolation valves? Can I function with them? Do I know how to open and close them? You know, lefty loosey, righty tighty, you know, just really get to know the system. And then before we start, we better check that rotation. A lot of pumps out there, and you should assume that all pumps out there, if you spin them in reverse, you could get into some serious trouble. Essentially, you may need a new pump, or at least an overhaul. So we want to make sure that when we check the rotation, this pump is disconnected from the driver, and we want to check the driver. So lock out the motor, open up the guard, and then disconnect the driver from the pump. Now, I've taken the whole coupling off here. Most of the time, you just have to take the flexible element, maybe the grid or the spider out. Then put back when you can. I would say all the time, put back the guard and bump the motor. Obviously, it's kind of hard to see sometimes, but you know, there's the motor fan in the back, possibly, or you can see through the guard. Many of these guards have inspection holes. So always put the motor, the guards back in place whenever you energize any of this equipment. I read the manual. Here, we've got a guard, lock out the motor. Oh, we've got V-belts. Okay, let's take the V-belts off. Let's put the guard back on and bump the motor again. This way, for sure, if there's ever any issue with warranty, you take a picture of the element, flexible element taken off, and you go back to the distributor or the manufacturer, say, yes, we did bump the pump, the motor, not the pump, to check rotation. Okay, making sense of pressure gauges. So pressure gauges, like I said before, are very crucial. Doing a pump startup without pressure gauges, suction and discharge, you're blind. You're really just checking for leaks. That's all you're doing. So discharge minus suction will always give you the total dynamic head of the pump. So let's have a look at an example here. 70 PSI on the discharge side of the pump. And let's say we have 5 PSI on the suction side. So that means that the pump is actually developing 65 PSI, 70 minus 5 PSI. You just got to think think of a pressure as an energy. Coming into this pump, the fluid already had 5 PSI integral to it. The pump then boosted it up to 70 PSI, but it only really had to add 65. So discharge minus suction is always the total dynamic head of the system, of the pump and the system. So now total dynamic head is 65 PSI. I'm really written something there that's very confusing and can get you into trouble. I'm speaking about total dynamic head, and I'm giving a pressure value. You know, many times you'll get away with this sloppiness, but when it bites you, it will bite you hard, because actually head is equal to a pressure times by a constant divided by specific gravity of the fluid. So in imperial units, feet of head is equal to pressure, PSI, times by 2.31 divided by specific gravity of fluid. Let's say it's 1 for water. And in SI units, in metric units, meters of head is equal to kPa times by 0.102 divided by the specific gravity of the fluid. Let's say it's water again. Now, where this comes into play is here we have a centrifugal pump curve, and down the top side that is in yellow right now is showing a pressure, so showing meters ahead, pressure PSI, and then ahead again in feet. That PSI truly is a bit questionable because it does say total head. But let's take a look at what this pump has been calculated on. This curve has been calculated on. It's calculated on a specific gravity of 1, or water. Therefore, let's choose a pressure value here of 28 PSI. Now, if we put that into the formula, 28 PSI times by 2.31 divided by the specific gravity of the fluid gives us about 65 feet of head. And if you take a look here, that 28 PSI more or less comes up to about 64, 65 feet of head. Great. What happens though, if we have the exact same pump, but this one now has been tested on a specific gravity of 0.8, or your value of your fluid isn't water. Let's take a look at this example first. 28 psi, all of a sudden, on 0.8 specific gravity, it would be 28 times by 2.31 divided by specific gravity of 0.8. It works out to be what? About 80 feet. So you can see a little change in specific gravity, it's not little, it's quite a bit, is going to change the relationship between pressure and head. Let's take a look at those two curves again, but just chop out the vertical. Specific gravity of 1, that was the first curve we looked at. Specific gravity of 0.8, that's the curve we just looked at. Take a look what's common. The head is common. It is always common in a centrifugal pump. If you take a look at that, where that 3450 RPM curve hit shut off, zero flow, it's about 55 feet on the specific gravity of 1. It's also about 55 feet on a specific gravity of 0.8. But look at the pressure. The pressure was about 25 psi here and about 18, 19 psi here. So if we were just taking a psi value, a pressure value, and not converting it, it makes a difference which curve we're looking at. And it makes a difference what we're pumping. So converting pressure values to head makes you look at the specific gravity. That's the lesson here. What do you think, Chris? Does that make sense? It's always a bit in the weeds.
No, I think it makes sense. Take a PSI reading on your gauge, but just make sure you understand that fluid and make sure you know the specific gravity of that fluid prior to taking your gauge reading to the pump curve. Exactly.
Most of the time, we probably get away with it because most things that are pumped in this world are water-like, but it's the times when you don't get away with it, it gets you. Okay, so now let's take a look at another case. Let's look at when our suction is negative. We're pulling a vacuum for whatever reason, 70 psi. And now we're pulling a vacuum of minus 5 psi. Well, 70 subtract minus 5, two negatives equal a positive, it's 75 psi. Just be careful of that. Don't let that throw you off. Just if you always remember, discharge minus suction is going to give you the TDH of the pump. Okay, we won't go through the changing that out into feet of head, same thing. So multiple pumps. Multiple pumps is if you're going to have a problem with a pump system, it's definitely magnified when we start to have more than one pump in that system because they start to interact with each other, especially if they're supposed to run together. And a couple of things that you first have to look at with multiple pumps, and Chris and I were just speaking about this a couple of hours ago. Are these multiple pumps, let me just throw some up here. Are these multiple pumps supposed to just run one at a time and they should never run together? How do you know that? Chris, how do you know?
From a design perspective, a control panel perspective, understanding the application.
Exactly. Understand the application. Maybe these pumps should always run together and one should never run. Who knows? So you have to really understand that application. And when you go to commission, start, or troubleshoot, make sure that you're running the pumps the way they were intended to run. So let's take a look at these two pumps. And they've both got individual suction lines. So the pumps are not operating right now. And we have a tank in front of these pumps. And the level is there. And the suction gauges are on these pumps. And we've got the suction gauge. And that suction gauge is going to correspond, if all the valves are open on the suction side, to the static head on the suction of this on these pumps. So whatever that is, say that suction gauge right now is a compound gauge. It measures both vacuum left of the zero at the top and right a pressure value. Right now is reading a pressure value because there's a static head over the top of these pumps. If that value changes, that level changes, the gauge will change. So with the pumps turned off, gauges tell you just as much information as when the pumps are turned on. Many times, I know Chris and I, we do this a lot. We want to know the values of these gauges before the pumps are ever running, right, Chris?
We do, yeah.
It's really important. Now, let's go back to the regular level. What happens now when we start the pumps? Let's start the pump. Inevitably, when we start the pump, even though the suction gauge was showing a pressure value, a positive value, or it didn't necessarily have to show a positive value, it showed a certain value. When we start the pumps, that value will become less positive. We're going to start subtracting things like friction. Remember, a gauge shows us two things. It shows us statics, vertical heights of fluid, and frictional values. So here, friction value is taken away from the overall static head that's pushing down on that suction gauge. If we pump more, increase the speed of these pumps, they start to pump more, we're going to get more and more friction, and we may, who knows, go into the pulling vacuum stage. We may go into the negative gauge pressures. Again, the level may not have changed in the tank. Maybe the level even went up. It all depends on how much friction was involved. So let's take a look now at one of these pumps. And let's take a look at that suction. That suction has its own system curve. Every piece of pipe, every valve has a system curve. And all what a system curve is how does the losses vary with respect to a varying flow? Well, in this case, no flow, zero friction. We show a value here of a positive pressure or a positive head. That's because this system curve starts below the flow curve. This is all showing as losses. This positive head here is showing as losses. Well, we don't have any losses to begin with. We've got a positive head. So therefore, this system curve actually starts below in the negative head region, or negative losses, in a sense. And as we start these pumps, or this pump, we're going to start to run up that curve. And if you take a look at that gauge, we start to subtract from that gauge all the time. And we'll get to a point in the middle where the frictional losses and the static head cancel out. Then, if we pump more, we're going to start to pull a vacuum. Really important to understand that even though a pump is flooded, we could still pull a vacuum. Let's look at the discharge side. This discharge is in series with the suction. Easy definition for series piping is whatever flow goes through one has to go through the other. That would be series. And again, this gauge starts out relatively high, maybe. It's representing at zero flow the static head above the gauge. In this case, it's to the header, from the gauge to the header of the system. And then as we push more fluid through the system, we're going to pick up more and more friction. And that gauge is going to show us that friction. Hey, if we knew the flow at each one of these points, gauge reading and flow, we could plot on site that little system curve if you had a flow meter. Now, since they're in series, what we can do is we can add these two system curves together vertically, add them on top of each other. And that's what the pump is actually going to be pumping against in a total dynamic sense. So if we do that, we get this green line, and that is the total system curve. And if you see that green line right here is slightly below that discharge system because we had to take away a little bit. All this was taking away from that discharge system. So it was helping us. And then obviously, we've said this a few times, where the pump curve and the system curve cross is where the pump should operate. What's going to happen when two pumps start? Chris, what do you think is going to happen when two pumps start?
I guess that is going to depend on what the system curve ultimately looks like, but we're going to get more flow.
You will get more flow. You're right. Two pumps starting will give you more flow. But what's going to happen in the individual sense? What's going to happen to each of the pumps? You're going to get less flow, right? Each pump is going to give you less flow. You'll never double the flow. So if that first pump's doing 40 liters per second, you turn on the second pump, you're not going to get 80 liters per second combined. You might get real close if you're just pumping against static and very, very, very little friction. You're going to get close, but you'll never get double the flow. You're going to get close. And we'll just look at that in a second here. Let's take a look at the other example. This is where we've got a shared suction. Again, this is very common. You know, it makes for a nice clean fit. There can be some problems, but if correctly sized, it shouldn't be a problem in a flooded case anyway. So again, we've got some kind of a tank here that we're pumping from. There's a separation, a wall separation, and there's your level. Let's get rid of that tank so we can see. And then again, from that gauge to the level in the tank, whatever that static height is, that gauge, when the pumps aren't operating, is showing us that height. It's showing us just, there's no friction involved, so it's showing us the static head on the suction side. Now we start the pump. What do you think is going to happen, Chris, when we start this pump? What's going to happen to that suction gauge?
Most definitely, we're going to get closer to zero.
Yes, we're going to start subtracting the friction losses. And this is a good point to kind of just have a quick conversation about what's going to happen here when two pumps operate. What do you think, Chris? What do you think is going to happen when we have two pumps operating in this case? Obviously, they're sharing the same suction. What do you think the possibilities are?
I mean, certainly we're going to be pulling more flow through that single portion of that line.
Yes.
So therefore, our friction losses will increase in that portion of that single line.
It's a good point. They will definitely increase. Now, having said that, if you've got still, let's say you're doing 40 liters per second right now, in this case, one pump running. When that second pump comes on, we're not going to do 80 liters per second. So that one pump that was doing 40 liters per second is actually going to do something less, maybe 30, because it's being pushed back on its curve. So you can't say that the frictional losses will double in that suction line. It all depends on the discharge again, how that discharge piping will allow these pumps to pump, essentially. So it's kind of a mix, but definitely two pumps running, you're going to still get more flow through that suction line. Agreed. So we're going to drop off. Pumps, multiple pumps, different sizes. You know, maybe we've got a jockey pump here, right here. We've got a little upkeep pump that, you know, takes care of some of the smaller flows, depending on the system. So pressure in the pipe. Let's first of all think about what this gauge is telling us before we jump into that dissimilar pumps. Pressure in a pipe represents all the pressure in a pipe represents all the downstream losses and static. So let's take a look at this example here. This gauge right now at this one pump is measuring whatever that is. As we move down the line or downstream, watch what happens to this gauge. As we move down, if we were to keep drilling holes in this pipe and putting this gauge as further and further down, reinstalling it all the way to the end, we would see this pressure drop off. And that's because, remember what gauges measure. They're going to measure the discharge gauge anyway, the downstream losses, the losses that are about to happen. So as we run down the discharge piping, this pressure gauge is going to drop off all the way to zero, right at that free discharge point. Okay, I don't care if you got a nozzle or whatever else at that discharge point. When that liquid leaves the system, it is at absolute pressure. It is at zero gauge pressure. It may be coming out at high velocities, but its pressure is definitely atmospheric pressure. So all that had to be burnt off, and that gauge is going to show us that. So having that in mind, again, this pump by itself is running against a static head and then all the frictional losses. Now let's get the two pumps operating at the same time, the smaller pump and the larger pump. What's going to happen here? Well, let's first of all assume something. We're going to assume that the losses through each individual discharge branch is negligible when compared to the entire shared discharge system. If we don't do this, if we've got a large, long system, branching system that goes from the smaller pump, you know, it might, 50, 60 feet away, lots of filters and things and all sorts of valves and losses, and then it hooks into that main header, then we're going to have to work with that pseudo parallel system approach that we spoke about several webinars ago. But let's keep this simple. Let's say really the losses between the pumps and that main discharge header are negligible. Then what we can do is we can plot the smaller pump curve against the system curve and the bigger pump curve, the pump against the system curve. And again, these system curves should be the same because we've said, hey, it's negligible, the interconnected piping. So all we have to do now is plot both pump curves together and then add them in the horizontal to get a combined curve. That is that combined curve where it crosses the system curve is where the combined pumps will operate. So let's blow up this area up a little bit more and let's take a look real close. We have our small pump. Our small pump by itself will operate right there in that location when it's only running by itself. The bigger pump, the larger pump, it's not much larger, is going to operate right there when operating by itself. When both pumps operate at the same time, they will give us this value right here, total. And each of those pumps is going to be delivering, is going to share that flow at the same head, is going to deliver. We throw a line across horizontally, and where it crosses each of the individual curves is where each pump operates when the two pumps are operating together in parallel. This can be trouble. This could push these pumps, one of these pumps anyway, to what's called a low flow, high head situation, or recirculation or discharge cavitation. We've spoken about it a couple of times. And essentially, let's take a look at the damage that's induced here. Let's pull the rotating assembly, the impeller and the shaft out of the pump. And let's take a look at this thing. This impeller, let's say it's happily operating this pump on the right-hand side. What's happening now is we're getting a certain flow rate coming into the impeller, and it's being thrown radially outward. As we start to back up on the curve, because we're starting to pump against more resistance, we're going to pump less. And as we start to pump less, and we're going to keep pumping less as we start to back up on the curve, until a point where we start to pump so much less that we start to get turbulence happening on the discharge side of this pump. And turbulence to me, I don't know about you, Chris, but turbulence to me means high localized velocities, right? Is that what you're thinking about, like a day like we're having today?
Tornado, yeah, tornadoes, yep, high winds, yep, turbulence.
Exactly. If we keep pushing this, that turbulence gets extremely high, and it gets so high that we get low pressure. When the velocity goes up, we've said it many times in other webinars, Bernoulli's principle, as velocity goes up, pressure comes down. And it can come down so much that we're going to, in a small localized area, we're going to vaporize that fluid. And once that fluid vaporizes, it then moves to an area just maybe, a millimeter away where it hits high pressure and it collapses in itself. And we get cavitation. And just as a reminder what cavitation is, here's a vapor bubble. And all of a sudden, it's going to see some quick pressure applied to it, and it's going to collapse into liquid. And there we have 200,000 to 300,000 PSI. And that's going to do some damage. And that's going to, as you see here, it's going to eat away at the pump, okay? Right at the tips of the impeller if it's discharge cavitation, and also the casing. And all this because that small pump was happy, pumping along its flow until the bigger pump came on, started pumping through the same header, and started to increase all the back pressures because now there's so much more friction, and that little pump had to get pushed back on its curve, reduce flow, and it started to hit that left-hand side and started to induce recirculation cavitation. So again, if these two pumps were not designed to operate together, then make sure they don't operate together. Many times with a jockey, smaller pump and a larger pump, when they're operating, they don't operate together many times. It's designed that jockey pump to go offline before the big pump comes on. Any comments there, Chris?
No, you just said what I was going to say. Just make sure, again, you understand why it is you've done it. And that smaller pump may have been in a low, the large pump may not have got down to that low flow, so you put a small pump in place. So I was just going to say what you said, to be honest.
Excellent. Good. I'm glad you agree. How did we know where these pumps were operating again? We would have had a discharge and a suction gauge. We would have looked at it. We would have checked the motor or checked the pump. We would have then looked at the pump curve, and we would have said, oh my goodness, this pump is operating way too low, way too far on the left-hand side, high pressure, low flow. And it would have helped us out. It would have also helped us out to know maybe that we shouldn't operate these two pumps together. Let's look at suction lift pumps. They have their own positives and negatives. So we're dealing with the flooded suction. Now let's look way, way up, as the friendly giant used to say many years ago. And we have here a self-priming pump above the standard traditional end suction centrifugal. There's a self-primer, and there's the flooded suction on the centrifugal. It is nice, and I don't know if you guys know, but we do sell self-priming pumps, Gorma Rups. It is nice on a self-priming pump. It does get rid of a lot of the excavation requirements. Look at all that, and it could be even at a height where maybe flooding could never even occur. So if you take a look right here, you know, the control panel maybe had to be lifted higher. This motor maybe had to be special because there could be a flood in a lower chamber. In this case, if we get up high enough, if it is possible, sometimes it isn't. If it is possible, you know, control panel, maybe there's never any chance it's going to be flooded. Motor doesn't have to be anything special because there's no chance it's going to be flooded. But I think the big saving is look at all that excavation. Anyway, so as before, we're pumping from a tank that is controlled by some kind of level control system. Here we're showing some kind of ultrasonic. And right here is a self-priming pump. We've spoken about these several times, but they're out there. There's something very common. And they're a little bit different, and you've got to approach them a little bit differently than a standard centrifugal. Just going to know a few things. So here is a standard setup. We've got a self-priming pump, high and dry. We've got liquid. We've got a suction line, and we've got this air release line that's going back down into the wet well. And here we see the air release line again. And the job of this air release line is to release air that is being pushed out of the suction line. So when I start this video right here, we're going to see this impeller spin. And it's within water. Right now, this pump is primed. Someone's filled it up. And this suction line is completely empty. It's full of air. And the liquid level is up to this point right here. It's just like putting a straw in a drink. And when this starts, what's going to happen is this impeller is going to throw liquid outward, creating a low pressure zone. And atmospheric pressure is going to push this fluid in the tank, in this well, up the straw, up the suction line. But before this liquid can get to the pump, we've got to deal with this air. So there's a story. Let's go for it. So impeller spinning. We're starting to generate a vacuum. Atmospheric pressure is starting to push this fluid into up this straw, up this suction line. This air now is being pushed and mixed in the center of this impeller. Air water is being thrown out the discharge of the volute. The water's falling back down through that recirculation port and keeping this priming going. It's refeeding the impeller, and the air is being thrown outward and rises through the air release valve and back down into the wet well. And that's the priming process. And I think I was a little bit faster than the pump in this case, Chris. Many times it isn't that way. So again, we have a big casing. We've got to make sure it's filled before we start pumping. Now, a question that a lot of people ask is, does this have to happen every single time? Every time I start this pump, or this pump is called to start, does it have to prime and get rid of that air? And the answer is no, or it shouldn't have to, because inside the suction flange or spool of this pump, there is a flapper valve. And this flapper valve is just like your thumb over a straw. You put a straw in a drink, put your thumb over the top of it, and then lift that straw out of the drink. As long as you keep that thumb over that straw, you are not going to lose that fluid in that straw. It's going to stay in there. And the same thing that happens with this flapper valve. When we're priming or when we're pumping, this flapper valve gets out of the way, liquid enters the pump. When we stop pumping, the flapper valve seats again. Pumping, flapper valve gets out of the way, just like a check valve. Flapper valve seats again. Now again, we could be pumping something that's trashy. We could get a cigarette butt underneath there. There are times when maybe that won't seat. And that doesn't necessarily will lose suction. Not necessarily if we do a few things with the discharge, but we could. And these pumps have been designed, and obviously the calculations have been done that we will prime within 5 minutes at least. Okay, pump won't prime. This is very common with self-primers. Not common, but it is something that can happen from time to time. Read the manual, but I'll show you what the most common problem is. The pump isn't filled. You can't turn this pump on. It's a self-primer, traditional self-primer. You cannot turn this pump on not filled with fluid, it will not prime, okay? So let's say you've done some work on this pump. You've had to drain it. You've done the work, you've put it back together again, and if you forget to fill it up again, it's not going to prime. It's going to spin and it's not going to prime. It needs that liquid seal to generate that vacuum. So if that's the case, if we've got it primed, then the suction leak is the most likely cause for this pump not priming. And a suction leak can occur anywhere on the suction side of the pump. And if you think about it, as we push that fluid up the line, the atmospheric pressure is pushing that fluid up the line and that air is being pushed into the pump. That air, as we know, now leaves the pump through the air release valve back down to the wet well. If this is working fine, then the suction gauge is telling us all the time what the static lift is. So for instance, if we start out this pump, the suction line is completely empty, and we start the pump, that suction gauge should read 0. As we lift the liquid up, as that liquid is being lifted up that pipe or being pushed up that pipe by atmospheric pressure, that gauge will become more and more negative, and it will represent 2, 3, 4, 5, 6 feet, whatever that level is. As it comes up, you're going to see that gauge represent what the level is in that suction piping. If we have an air leak, if it's a small air leak, many times these pumps will prime. If it's a big air leak, we're going to have issues. What we're doing is consistently replacing that air with fresh air, and we're negating that vacuum that's being drawn. So how do we fix it? Well, we've got to find the leak. And I'd say, what, Chris, maybe 10–15% of the time on a startup, on a self-primer, there's a suction leak to begin with. Tighten bolts, you know.
Loose bolts, gaskets not seated properly, that kind of stuff.
I think one of the main issues is that discharge piping is many times tested, pressure tested. Sometimes the vacuum on the suction side, first of all, it's going to be seen a vacuum, but many times it's not even tested, the joint. So that can be sometimes a bit of an issue, but if you're ready for it, it's not a problem. So listen for hissing at the flanges. If there's going to be a suction leak, it's probably going to be at the flanges somewhere. So I prefer Gillette. Chris, I don't know what you prefer as your medium to spray on these joints.
The lemon flavored sensitive skin versions.
Okay, but it cannot be gel. It has to be foam. And we're going to foam up that joint. Okay, and we're going to start the pump. We're going to foam up all the joints. And what we hopefully will see is in a location that foam disappear and get sucked in to the leak. And there you got the leak. If you didn't hear it hissing, you'll hear it hissing this time because it induces the noise, the foam, all the foam being sucked into that leak. Also, cling wrap. You wrap all the joints with a little bit of cling wrap and then start the pump, and automatically you'll see that cling wrap suck around and get pulled in. And actually the pump will most likely prime for a while until the cling wrap disintegrates. So that's an indication of where the problem is. And that usually solves it, right, Chris?
Yeah, we've done it a few times and troubleshooting for sure. Obviously, as you said, I think you said, soapy water on a suction line isn't going to function. You don't get that bubble that you see on a pressurized system. So something that has some thickness to it, like shaving cream, just allows you to see that little tunnel being created from the vacuum in the foam.
Great point. Soapy water is great for pressure leaks. This is a vacuum leak. Good point. So now, what does it look like when this pump actually primes? Well, we're going to see the air release valve close. There's a spring there. It's going to close off. And we're going to see some value here, some suction value that will be the lift itself, the vertical measurement, the lift, plus a friction value. And then the discharge, we'll see some discharge pressure now, which has actually gone dynamic. We've got rid of all the air. We can energize that water and push it through the system. So the pump goes dynamic.
Something else to take away from that is, you mentioned it a couple of slides ago, is that vacuum gauge is going to give you the physical distance that liquid is up the suction line. So just having a physical understanding of what your measured suction lift is, at least then you can sit there and watch that gauge pull more and more and more vacuum, and you can visually say, okay, I'm at 3 feet now, I'm at 7 feet now, and you know that it's actually going to prime at 9 or 10 feet. You actually get a feeling of when the pump's going to start to see fluid from that suction line.
That's a good point. And then as soon as it goes dynamic, then we pick up the friction, and that can double the that can double that lift. You know, that's when it goes a bit crazy. But you're right. When we turn off that pump again, if there's no suction leaks, then that suction gauge will lose all its friction and show the lift that we are maintaining, that static lift. Yes. Let's talk about submersible pumps. Here we go. My submersible pump now. We've got it in the wet well, pumping down, pumping down. So it's on a base elbow. And as we've known before, that base elbow, it's a nice little arrangement here. If you ever need to do work on that pump, you can pull it up, those guide rails. The problem sometimes can be gauge location. Right here, you know, that's not all the system. The system goes on for miles maybe. Right here is probably likely where we're going to have a gauge. It's going to be a gauge that people can read. So it's going to be probably up top out of the wet well, or it doesn't make sense to have it in the wet well. So that gauge, again, as we know, gauges read all the losses, static and friction downstream. So it's going to read the static head from that gauge onward, and it's going to read the friction from that gauge onward. But what about all the rest of it? What we end up seeing is it's not reading this portion, right? It can't. It doesn't know what happened before it. The gauge tells what's going to happen, not what happened before it. So if we have a pump curve, submersible pump curve here, we know we're operating along this curve. And according to that gauge, at startup, commissioning, whatever, we should be pumping, we are pumping a certain amount. But in reality, we're pumping something less. Someone with a flow meter or someone who does a drawdown test goes, that gauge, something's wrong. We should be pumping a whole lot more. And that's because we had to correct that gauge. And we only can do it by some kind of estimation usually, because we don't have a gauge at the pump. We'd have to do the static is definitely something that we could correct for just with a tape measure, liquid level in the sump to the gauge, 10 feet, 20 feet, whatever it is, and then some frictional value. So be careful. Sometimes submersible pumps look like they're not performing the way they should be according to that gauge. And because the submersible pump, it's integral most of the time to the motor, we start to give you values. First of all, the efficiency. The efficiency is known as wire to water. This is almost all the time. And what this takes into account is the motor efficiency and the wet end efficiency together. So let's say the motor was 80% efficient. That's a terrible motor nowadays. And the wet end was 80% efficient. The total wet end wire to water efficiency would be 0.8 times 0.8. So it'd be 64% efficient. And that's what would be shown. You got to remember the pump manufacturer, when it's an end suction centrifugal without the motor, he doesn't know what motor you're going to use. In a submersible case, the manufacturer knows exactly the motor you're going to use. And therefore, it can give you a lot of information. It's usually the electrical stuff right here. It can tell you, the manufacturer can tell you what the amp should be at a certain voltage and a certain flow rate and head. I won't show you how to read this. They're all a little bit different. But essentially, there's a lot more information electrically on a submersible curve because the manufacturer knew exactly what the motor was going to be. Submersible pumps, they can't cavitate, right, Chris?
No, they're in the water.
Good point. They can't suction cavitate, or technically they can. Maybe they're not in the water, but more often than not, you're going to see if it's going to cavitate, it's going to be that recirculation cavitation again. We've got too much back pressure on this pump. There's too much resistance. There's too much static. This pump was sized too large. It's operating on the left-hand side of its curve. And again, that's going to induce these eddies, these low pressure, high velocity, low pressure areas where we're going to vaporize the fluid. And high velocity, low pressure. And we're operating on the left-hand side. So you may not hear the pump. Discharge cavitation isn't the loudest. Suction cavitation is much louder usually. You're not going to hear this, but you're going to shake, rattle, and roll the mechanical seal, the bearings, the shaft. You know, it's something you want to stay away from. Again, only way you're going to know this is gauge readings, and in this case, corrected gauge readings. And again, damage, very similar to any other pump, any other centrifugal pump. Use gauge readings corrected. Now, there's one other form, and we'll end it shortly here. There's one other form of cavitation that can occur in a submersible system. And this is a bit of a rare one, but I've seen it happen. And I've heard of many people seeing this happen. Take a look at the designer here. He wanted to make the operator's life real nice and easy. He did not want the operator going down into the wet well or going into any confined space to deal with valves. So what he did was, or she did, was put the valves all high and dry. Excellent idea. Until that high and dry is about 9 meters or about 30 feet. And then we get an issue, and it's a big issue. That discharge check valve is about 30 feet above or 9 meters above the liquid level in the fluid. As the pump shuts off, that discharge check valve, that little flapper valve, that valve closes. And now all this liquid is sitting up in the air 30 feet. Are we getting anything coming in from the, the comments, Chris, at all at this point? People guessing what the problem is?
No, not yet.
Okay, I guess I haven't asked. But let's do a mental experiment here. I like mental experiments. They're a little easier to carry out. If I have a big bucket of water and I put a hose pipe in it, a really long hose pipe, and it's submerged, it's full, and I pick up one end of that hose pipe and put my thumb over it, and I start to move up on a crane, and I keep my thumb over the end of that hose pipe, what do you think is going to happen to my thumb at about 10, 20 feet high? It's going to start to hurt because there's a vacuum being drawn. And when I get to that 30 feet or that 9 meters, I'm reaching the value of standard water at standard temperatures, 20 degrees Celsius or whatever, the vapor point. And I'm going to vaporize the fluid underneath that check valve. Now, it's not going to take long. It'll vaporize and it'll balance out. But then we've got vapor. We've got negative pressure right there. And the next time that pump starts, boom, we're going to get hydraulic hammer. And I have seen pipes shake all over the place due to this. So again, it's not even a submersible thing here. If you ever put the first check valve after the pump at values of 9 meters or so, atmospheric pressure essentially, then you could run into this issue. Secondary and check valves after that will not have this issue. There are some standards to say, hey, don't put them too far apart as far as a height perspective goes, but it's that first valve that causes the issues. And finally, to end it off here, air entrainment. It is not cavitation. It can happen in any pump, and it's usually slight growling or even noise depending on the pump. And the way you know this is usually those gauges are bouncing. You're not getting steady, even expensive gauges are going to bounce. You're not getting steady readings. And your amperage reading will come down. The amount of work that pump is doing is going to be less than expected because it's now throwing air. It doesn't weigh as much. It's easy to throw air, okay? We're displacing fluid. We're not doing as much work. And Chris, I don't know about you, but I have a tough time sometimes looking at an impeller. I know cavitation, I know the forms, but sometimes damage due to air entrainment can be difficult.
It can. I mean, I would expect to see it more overall, the impeller, as opposed to localized like cavitation is. But, you know, it is tough to sometimes differentiate between the two.
It is. I agree. Best way is to know what were the gauge readings in the field, what were the drawdown tests, flow meters, you know, what the values were. And again, that humming, that noise. Any questions? We didn't get to... Yeah, we didn't get
actually, which we've probably got time to answer.
Yeah.
What would happen if the water in the pit is 80 degrees C? Would the submersible pump possibly cavitate?
80 degrees C, first of all, there are some submersibles out there, but that motor under 80 degrees C is probably not going to be happy for most submersibles. So you're going to have a motor issue first. That motor wants to get rid of heat. So it'd have to be a special submersible. 80 degrees C, water boils at 100. It could, depending on how much the pump is pumping and the losses in that intake location. We could have an issue. All depends on the depth of the fluid too. I would definitely watch an 80
Generally,
degrees.
we say submersibles don't suction cavitate, but you're going to get to a point on that liquid level, as Steph says, where you're so close to its vapor pressure based on the temperature that you could actually, I guess, suction cavitate at specific temperatures.
Sure, the liquid's already almost vaporized. Yeah.
What happens to brake horsepower when the specific gravity of the fluid is not 1?
Good point. So you want to answer that, Chris?
Thanks, Adrian. You're gonna need more horsepower to move that fluid if it's heavier than water.
That's right. Yes, and it's going to be a linear relationship.
So at an SG of 1, you might need 10 horsepower. An SG of 1.2, you're going to need 20% more horsepower.
Yes. Yes. Good.
Will the seminar be available for downloading or viewing? Yes, it's on YouTube, on John Brooks's YouTube channel, along with basically all the other videos and other filtration and other webinars that have been done by John Brooks. That's all on our website.
This one will probably take a day or 2. Yeah.
Okay, so that's it, I think.
Yeah. Yeah. So I appreciate it, everyone. Again, we'll probably see you in 2 to 3 weeks with another technical webinar, and we really appreciate the time that you're taking to join us. Thank you.
Thanks a lot.